Okay, so in today's lecture we will discuss potential formulation of electrodynamics. So the topic today is potential formulation of electrodynamics. Okay. Now in electrostatics we have we have curl of E, that is the curl of the electrostatic field, is equal to 0 in electrostatics. Now this implies that this electrostatic field can be written as the gradient of a scalar potential. But in electrodynamics, curl of E is not equal to 0. Curl of E is not equal to 0 in electrodynamics. So, only a scalar potential is not sufficient to give us the electric field in case of electrodynamics. Okay. Now, in electrodynamics, this condition is still valid, that is, the divergence of the magnetic field, this is 0. So this condition remains valid in electrodynamics. So we can write this magnetic field B is equal to curl of a vector quantity, that is the magnetic vector potential. A is the magnetic vector potential. Okay. So in electrodynamics, magnetic field can be written as the curl of the magnetic vector potential. Now we will see how electric field is modified in case of electrodynamics. Now, from Faraday's law, that is the Maxwell's third equation, we know that from Faraday's law, we have del cross E is equal to minus del B del T. Okay. Now we will put in place of B that this del cross A. Okay. So we will put in, so del cross E is equal to minus del del T of del cross E. Del cross E. Okay. Now since this is partial derivative with respect to time, and this is the partial differential vector differential operator with respect to positional coordinates, so they are independent, so I can interchange them, so I can write it as del cross del A del T. Okay. Now I can bring this term on the left hand side and combine with this term, so or del cross E plus del A del T, this is equal to 0. So in electrostatics we had curl of E equal to 0, but in electrodynamics we have curl of E plus del A del T, that is equal to 0. So therefore this can be written as the gradient of a scalar function. So we can write, so this implies that E plus del A del T is equal to minus gradient of a scalar potential. So in electrodynamics we have E vector is equal to minus grad V minus del A del T. So this is how the electric field is modified in case of electrodynamics. Okay, now we will see the Maxwell's first equation and fourth equation, those containing the source terms, how those equations are written in terms of this scalar and vector potential. Okay, now Maxwell's first equation, is del dot E is equal to rho by epsilon 0. Okay, now in place of E I will write this expression. So or del dot minus grad V minus del A del T, this is equal to rho by epsilon 0. Now I can take minus sign on the right hand side, and del dot grad V is del square V, and I can insert this del operator inside the time derivative. So I can write or del square V, this is the Laplacian of V, plus del del T of del dot A, that is equal to minus rho by epsilon naught, epsilon 0. So this is how Maxwell's first equation is modified. Okay, so we write the Maxwell's first equation here, that is del square V plus del del T of divergence of the magnetic vector potential, this is equal to minus rho by epsilon 0. This is suppose equation number 1. Okay, now we will see how Maxwell's fourth equation is written in terms of this scalar and vector potentials. We will see. Now Maxwell's fourth equation is curl of B del cross B, that is equal to mu 0 into current density vector mu 0 J plus mu 0 epsilon 0 del E del T. Okay. Now in place of B I will write del cross A, and in place of E I will write minus grad V minus del A del T. So we get or del cross A, that is equal to mu 0 J plus mu 0 epsilon 0 del del T of minus grad V minus del A del T. bracket close. Okay. Now this del del t I can insert inside this del operator. So, and in the left hand side I have del cross A, that I can use this vector identity. So this is gradient of divergence of A minus del square A, that is equal to mu 0 j, then minus mu 0 epsilon 0 gradient of del V del T then minus mu 0 epsilon 0 del square A del T square. Okay. Now I can bring these two terms on the right hand side and this term on the left hand side. So, or minus mu 0 j, that is equal to, now I will write first this term, so del square A. Now I can combine this gradient of divergence of A with this term, so this becomes plus, no, when this comes in the right hand side, this becomes minus, so minus gradient of bracket divergence of A plus mu 0 epsilon 0 del V del T bracket close. So now this term, so minus mu 0 epsilon 0 del square A del T square. So Maxwell's fourth equation is written in this form using the scalar and vector potentials. Okay, so I need this equation. This is suppose equation number 2. So I am writing here Maxwell's fourth equation in terms of the scalar and vector potentials. So we have, therefore, del square A. Now I can write this term. So minus mu 0 epsilon 0 del square A del T square, then minus gradient of bracket divergence of A plus mu 0 epsilon 0 del V del T, and that is equal to minus mu 0 into current density vector J. So this is equation number 2. Okay, so this is Maxwell's first equation and this is Maxwell's fourth equation, which are written in terms of scalar and vector potentials. Okay, now these two equations contain all the information of electrodynamics. These two equations, that is equation number 1 and equation number 2, these two equations contain all the information of electrodynamics, but this scalar potential V and vector potential A are not uniquely determined by these two equations. because we can impose some extra conditions on V and A. So these two equations do not uniquely determine V and A. Now we can always impose some extra conditions on V and A. So we can impose extra conditions. We will see how. Extra conditions on V and A. Okay, so now we will see how do we put the extra conditions. Suppose A is modified to A dash, that is equal to the old A plus a vector quantity alpha. So this is how we are modifying the vector potential, and V is modified to V dash equal to V plus beta. This is a scalar quantity. So this is how I am modifying the vector and scalar potentials. Now the constant is that this newly defined vector and scalar potential, they should agree with the old E vector and B vector, that is the electric field and magnetic field. They should not change under this transformation of A and V. So E and B should not change under the above transformations. Under the above transformations, electric field and magnetic field, they should not change. Okay, so curl of, so let us see what does that imply. So del cross A dash must be equal to del cross A, and that should be equal to B. This is the constant. This A should obey. Okay. Now A dash is A plus alpha, so I can write down del cross A plus alpha, that is equal to del cross A or del cross A plus del cross alpha, that should be equal to del cross A. Now I can cancel this term and this term, so this implies del cross alpha is equal to 0. So this condition we get. So since the curl of this quantity is equal to 0, I can write down alpha as the gradient of a scalar quantity, that is suppose lambda. So this implies alpha is the gradient of a scalar quantity lambda. Okay. So we have seen that if the magnetic field should remain same, then alpha should be gradient of a scalar function, that is lambda. Okay. Now let us see what electric field implies. Now minus gradient of V dash minus del A dash del T is the electric field in electrodynamics. That should be equal to minus grad V minus del A del T. This is also the electric field in electrodynamics. So the newly defined scalar and vector potential, this gives the same electric field which our old V and A give. So now in place of V dash, I will write minus gradient of V dash. Now V dash I have written V plus beta. So V plus beta minus del del T of A dash, I have written A plus alpha. That should be equal to minus grad V minus del A del T. Okay. Now this minus grad V, so or we obtain minus grad V minus gradient of beta minus del A del T. Okay. Now alpha, I have obtained gradient of lambda, so I can write in place of alpha, I can write gradient of lambda. So minus del del T of gradient of lambda, that should be equal to minus grad V minus del A del T. Okay. Now I can cancel this term and this term and this term and this term. So we get